Okay, right here we have x of t, and the corresponding Fourier transform is x of f. We have the sampling as consisting of an impulse train, and the Fourier transform is another impulse train in the frequency domain. And the resulting sampled signal, you can see here, is comes from multiplying x of t with this impulse train right here. Okay, so what's the Fourier transform of this? Well, you can see it consists of multiple spectra of the original signal. Now, this multiplication in the time domain corresponds to a convolution. Convolution between what? Between the original signal and this impulse train. So when I convolve this with this impulse train in the frequency domain, I get multiple spectra of the original signal. That's an important concept that you really need to understand. Whenever you sample a signal like this, and you get this right here as x of st, you get multiple spectra of the original signal. So in summary, what we have is the original message and its corresponding Fourier transform, a periodic sampling function. In this case, we'll consider it as an ideal impulse train, and we have its corresponding Fourier transform. Then we have the sampled signal of the original message, and we see that its Fourier transform consists of multiple spectra of the original signal. Equation-wise, we saw that it was a convolution between x of f and the periodic pulse train in the frequency domain, resulting into multiple spectra of the original signal centered at the sampling frequency and its harmonics. What I'd like to point out in this case is that instead of an ideal impulse train, we have a periodic pulse train. So there's a certain width as compared to an infinitely small width for the impulse train. And you can see here, instead of in the frequency domain for this periodic pulse trains, the heights are not equal but follows the envelope of a sinc function. Okay, whereas we saw in the impulse train, the heights are it's equal height. Okay, so instead of these multiple spectra being of equal height, it's convolution between here, the original message in this frequency domain, and this impulse set of discrete set of frequencies centered at Fs and NFS as before, except the heights are different. And that's why you have multiple spectra that are not of equal height. Okay? So how do we recover the message from this sampled signal right here? Okay? How do we go from here to here? Well, the only difference is that you have to get rid of these multiple spectra if you want to recover the original signal. And the best way to do this is an ideal low-pass filter. Sometimes we want to oversample, because what happens if we sample at twice the highest frequency? These spectra will spread apart, and therefore our stringency or constraints or requirements of the low-pass filter is more relaxed instead of this steep filter, so that we don't get any of the other multiple spectra. We want to get the one here centered at baseband, basically. So that's how we recover our original message. Again, another illustration of how to recover the message and then the overlap of multiple spectra when we don't sample at twice the highest frequency. Here we recover the message by low pass ring filter on the spectra centered at the origin, and we get rid of the multiple spectra. Okay, so we can see here that Fs minus Fm implies that Fm right here has to be less than, if you look at this, that point must be Fs minus Fm. And then from there you can get sampling twice the highest frequency is the criterion if you don't want overlap between these multiple spectra. So as we increase the sampling frequency, this spectra starts to spread apart, and this filter can be more relaxed. We can go from a higher order to even lower order. Okay? This is the figure here, 27b, is when we don't sample at twice the highest frequency and we have low frequency effects right here, called aliasing.